to the podium and let's start and kick off the session. Ameria, come to the podium, please. Thank you.
Good morning, everybody. Good morning. Okay, I'm so delighted to stand here in front of you. I'm the first session of the second day moderator. My name is Ameria from Tanzania, East Africa. My professional is a mapping officer and land surveyor. I have a bachelor in geoinformatics, and I have a Master of Science in GIS. I work with the Ministry of Lands, Housing and Human Settlement Development like 16 years now in the land field and in the mapping experience. Today I'm going to share my geospatial experience where I'm going to link the geospatial and basically in the space technology with the groundwater resource management. Please let us listen to one person or presenter online. The name is Hafsa Ayman from China, University of Wuhan. Please, Hafsa, we are on time. Please welcome and proceed. Thank you.
Thank you. Thanks a lot. So let me start with my presentation. So the topic of my today presentation is more about the assessing vulnerability of agricultural dependent communities to the climate change impact on groundwater. So today I'm going to present a case study in one of the district of Pakistan, which is Okara. And this presentation is going to have a kind of vulnerability assessment related to groundwater while integrating the factors of exposure, sensitivity, and adaptive capacity that we have implemented for this approach. Next, please. Okay, so the content of my presentation is split in a way that in a first component, I'm going to tell you about my research work and its significance, and what are its objectives behind it, and what are the materials that are being implemented to carry out this objective, and what are the results and how they're contributing toward the assessment. And lastly, I'm going to discuss with the way forward. We're working in developing the kind of groundwater management information system. Next, please. So about the climate change and geography of Pakistan. So the area that Pakistan is actually possessed is 796,000 square kilometer. And this area is also the summer monsoon accounts like most of the time with around 60% of its total area with received annual precipitation. And third-fourth of this country receive rainfall of less than 250 millimeter. And this region is also known as the sixth most populous country, and more than 37% of its area comprises with urban and settlements. And this area, due to climate change, is now more sensitive to the climate change threats that we have been facing from the past few years. Like we have the drought, then we have the flood, and how these variations in climate change are actually impacting the agriculture related sectors to it. Next, please. So what we talk about the climate change impacts on rural communities. So yes, they exist. when we have a rise in temperature, when we have the extreme events. So in that scenario, then the water scarcity come that is being gradually increasing, and this is like one of the potential the phenomena for the many regions. For example, in the case of Pakistan, when we have the kind of insufficient volume of water and we actually do not have idea about when and where we need to use it. So like in that scenarios, when we talk about the farmers, they are the main respondent who are actually been impacting due to this climate change. And yes, their livelihood associated to it, so that is definitely also impacting. Next, please. So about as far as my research significance is concerned, so my research significance is going to have the following objectives in terms of its impact. Next, please. So in research significance, we are taking the area of like Pakistan we are working on. This is only like the like already the water stress region and highly susceptible to the adverse effect of climate change, and as well as the economy that will actually depend on it and how its natural resources are being affecting due to it. Next, please. So my research significance is going to indicate what are its impact on agriculture productivity, and most importantly, the groundwater challenges that we are facing with regards to it, and how the communities are at risk, and what are the gender barriers that could be like affected or are in like playing a very critical role when we talk about the adaptive capacity in that scenario. Next, please. So my research objectives are going to have the following components. Next. So the focus of my research are based on the following components while utilizing the existing data that we have collected. Next, please. So in that scenario, what we're doing is try to identify the extent of groundwater related challenges that we are facing in that particular area. So in this way, so our research is going to utilize the GIS based risk mapping to rank associate those factors that are actually responsible for this vulnerability, and we're just trying to also map out and review the action plans which are actually supporting the addressing the climate change induced vulnerability related to the groundwater. Next, please. So my research is going to indicate that what are the climate challenges, what are its rural implications when you talk about the communities, as also like indicated into it, and how we can integrate to come up with a kind of action plan with the proper water resources management while utilizing the satellite information, while utilizing the information that is being present that are being collected from the field directly, and how we can do a kind of monitoring assessment for the future like sustainability analysis. Next, please. Next. Next. So this is like the overview about my study area. So we have chosen the area of Okara. So this area is well known for its diverse variety of crops, and this area is also lies interflow between the two major rivers of Pakistan, which is Ravi and Satluj. And agriculture is a primarily economy activity in this region. Next, please. But now this area is like prone to the groundwater challenges, and there are various factors, and the land change pattern is also one of its factor which actually relevant to from the past few years for the overexploitation of groundwater usage. And geographically this area is vital for driving the baseline indicators for the land use change, and there is actually the need for developing the kind of strategies for the sustainable groundwater management in this area. Next, please. So the data collection that we have been done for this study is we have utilized the extensive data sets. So firstly, from the spatial Earth observational data sets, we have utilized the Landsat time series, and due to its good temporal resolution. And then we also integrated the kind of existing land cover atlases that exist, and we're also trying to implement the climatic parameters, how the precipitation is been changing in this area. So what is the temperature is going on in this area, and what is the quality of soil, and how it is linked with the land use land cover. And most importantly, what we have done is kind of collecting the information relevant to the groundwater tube wells, where it exists, what are their distribution, and what are their operational time during different seasons, and what could be the discharge of using those tube wells for the agriculture practices. And most importantly, from the field observations, we're taking the farmer perception, what they think, how the climate change has been impacting to their area as well. Next, please. So this is the kind of like the ground truth survey we have been conducted, and I've been a part of it. We're just trying to collect the information about the groundwater table depth, how it's declining from the past year. I'm just trying to geotag the cropping area where it exists, and we're actually trying to have a discussion with the community, especially the female farmers, how their actually role exists in terms of while making their decision in water and agriculture as well. Next, please. So we also trying to indicate what are the constraints specifically the female farmers while they are where actually they are facing, and what are the factors that are actually limiting their capability or the capacity while we talk about the decision making in agriculture and water. Next, please. So this is like some of the spatial representation of the data sets that we have utilized. So the left panel is indicated that the variation in groundwater table depth, and the blue region is indicate that the area where is actually the declining groundwater we have been observing. And the right side panel is indicate that the spatial extent of the land use land cover, where the green area is indicate, okay, this is the agricultural land, and what are the area where the tubal density is high, and how the quality of the soil is been changing in this area, and how the topography on this region. And this is like some of the spatial representations of the spatial a few of the indicators that we have used for the kind of our further variability analysis. Next, please. So what we did is we actually combined all those factors relevant to the groundwater and associated factors, and we have done a kind of variability analysis so that we can get some assessment. Okay, this is the area which is actually facing the kind of variability in all these parameters. So this is the area which is where the actually groundwater is depleting in a very fast rate. So we actually combine all these factors, including the what we get from the ground truth and what we get the satellite, and we pass through the kind of variability matrix, and we come up with the kind of hotspots, which indicating, okay, this is the area which needs to be prioritized. Okay, this is the area which is more prone to the groundwater depletions, and this is the area which needs to be prioritized for the future action plan. Next, please. So when we talk about the results and finding, okay, this is the kind of spatial vulnerability risk assessment. So we came up actually the kind of the areas which are actually facing the highly groundwater depletion rate, and where the tubal density is high, where the table declining is a very fast rate from a past few years. And we have like come up with the results that the 35% of this area of Okada, okay, this is the area which is facing severely groundwater challenges, and 20% areas it shows, okay, this is the moderate to a low area. Okay, this area is maybe like sometimes don't need to be prioritized for the further action. So our finding is actually providing support to the especially to the agencies and relevant to the water sectors in a way that they can do a kind of implementing strategy for safeguarding their groundwater resources, and they can promote a sustainable utilization in that specific area. Next, please. Okay, this is the kind of spatial distribution that we have made from the last 10 to 15 a year, how the agriculture pattern is being changed, and where are the crops they exist. And we have come up with a kind of, okay, 6 major crops is indicated in this area. And we have done a kind of phenological cycle. Okay, this is this signature, or maybe this phenological cycle is correspond to this crop. And we come up with a kind of final, our detailed crop-based land cover. Next, please. Okay, so our key results is actually indicated majorly the change in a land use land cover pattern, which was recorded to reduce significantly between 2000 and to 2022. So it was like reduced from 91% to 80%, and further to it, we have observed the increase in the built up area. And when we talk about the gender priorities, yeah, it actually exists. So in that purpose, we have did a kind of baseline assessment and the baseline survey in that area. So we come up like, okay, the 2% are the ratio of the women they are engaged in decision support, they are engaged in decision when we talk about the agriculture water, they are participating somewhere in this. So our like funding is also providing the preventive measures for the vulnerability information into the policy decision making process that require the special protection. Next, please. So what we're doing in that regard, so after the hotspot analysis, so we actually mark those areas where we have started deploying the groundwater monitoring sensors, so at least we can get the real-time information about the water table depth, its conductivity, water conductivity, temperature, as well as its pressure, hydraulic and the atmospheric pressure. So at least we also made a like equal dissemination so that we can cover the overall area, but the red regions are very important to us, and we also actually try to make it more prioritized for the installation of this sensor. Next, please. So in the end, what we are doing is a kind of developing the comprehensive information, whatever we collected in this area about the groundwater tube wells, their tagging, where they exist, and how we can combine, how we can synthesize the information coming from the CTD divers, which is ground monitoring sensor. So we're developing a kind of comprehensive groundwater management information system. Next, please. So this is one of the screenshot of the GMIS system where I'm working on. So what we are doing is trying to synthesize the information, whatever it's coming from the groundwater tube wells, what are the agriculture tube wells, where it exists, what are their time, either they are operating on ignition, electrical tube wells, and what are the distribution of drinking and industrial tube wells. So actually we are still in a process to getting into the information, and we're trying to incorporate this information into this dashboard. And we also like now in a phase for getting the information relevant to groundwater quality. Okay, where are the areas where the arsenic hotspots exist, and how we can prioritize all those areas. There is actually need a kind of action plan for the safeguard of our groundwater management information system. So next, please. So our way forward and new insight. Next, please. So in new insight, we actually did a kind of comprehensive assessment combining both the qualitative and quantitative information. Okay, we did the focal group discussion, we did the ground truth surveys, as well as we try to head interviews with the communities directly, and I'm a part of it. And this is something that we're coming up with the kind of the vulnerability assessment, and it's a way forward. So next, please. Okay, so in way forward, we are looking into like this is like the major four component where we're looking it. In terms of policy implications, we are looking into their impact to the local communities and the well-being of it. And secondly, we are also looking the adaptive capacity in terms of women empowerment, how we can build their capacity where they think they don't have the resources to the specific capacity building programs, where how we can empower them, how we can encourage them to come okay to participate in it. And in terms of land climate change adaptation is also like one of the factors where we're looking into it in terms of way forward. And then we are doing a kind of similar studies to those areas which are facing similar challenges. For example, we are trying to replicate the area where we're working on in Punjab. We're trying to replicate it from the other district. So this is the kind of like the information so that we can develop for the our sustainability of our groundwater at least development through developing these dashboard systems. So I think that's all. Next, please. Thanks everyone for your attention.
Thank you, our first presenter. The first presenter was Hafsa Aman, who is working with a senior research officer, geomatics at International Water Management Institute, IWMI. She is pursuing a PhD degree in photogrammetry, remote sensing from Wuhan University, China. And now is the time for questions. If there is online questions, please. Okay, thank you. I've been told that the questions will be at the end of the presentation of this session. So please welcome the second. Okay. The next presenter The next presenter is a lady from Tunisia. Her name is Badia Cheli, a Water Research and Technology Center. But she will introduce more herself when she starts speaking. Welcome, Badia.
I can use this one. Okay. Good morning, everybody. Good morning, everybody. I am Mrs. Badia Chouli from Tunisia. I am working in Water Research and Technology Center that belong to Carthage University in Tunisia. I am a teacher and researcher in this center, Water Research and Technology Center. I am hydrogeologist. Today, I will talk about, in my topics, I will talk about the use of space technology for water management of transboundary groundwater sharing between Algeria, Tunisia, and Libya in North Africa. Yes. You have to go to the computer. When you click the computer. I should go there. Right. Just assign the computer. This computer, okay. The aquifer that I will talk about, it is the Northwest Sahara Aquifer System, is called in French SAS project. It is aquifer, underground aquifer and fossil aquifer composed by two superposed aquifers, the continental intercalaire and the continental intercalaire, the complex terminal and the continental intercalaire. It is an area about 1 million kilometers cube shared by three countries, Algeria, Tunisia, and Libya. The population in this area is grow about 4 million in 2000 to 8 million in 2030. It is irrigated land and intensively exploited resources. It is a fragile ecosystem and very vulnerable environment. Here you have the survey of exploitation in this aquifer from 1916 to actually the number of the water points increase, and it is about 9,000 sharing between Drel, Well, Spring, and Fugara, and shared between these three countries. This project, or the SAS project, is hosted by OSS. It is Observatory or Sahara and Sahel Observatory, Observatoire du Sahara Septentrional, sharing between these three countries. The Sahel and the Sahara and the Sahel Observatory is a solidarity platform. Platform in the service of sustainable development in Africa, is a Tunisian based international and intergovernmental organization established in 1992. OSS action is focused on two major topics, land and water. It's for environmental monitoring, especially for desertification and water resource, in particular shared water. The project, or the SAS project, is implemented by different phases. The first phase is start in 1999 to 2002. And especially in this phase, what we do, the establishment of the common-based database, the development of the information system, and the construction of the conceptual model. And we try to make common data from all the scientific do research in this area, using all the approach, the geological approach in this area. Then we do modeling. And the second part, it was installation of the consultation mechanism between these three countries. Here, example of the simulation modeling that I do for the continental intercalare to see the artesianism decrease from 1915 to 2015. The simulation model based in the model allow us to mapping vulnerable map that you can see the zone more vulnerable, and it is what you can focus the more study in this area. The second phase is concentrated in the estimation of the diagnostic of the agricultural practice in the SAS, and the setting up the institutional consultation mechanism between these three countries. The third phase is structured around the two main components: the socioeconomic study. The objective is the analysis and understand the irrigation behavior for the irrigator in this for a better valorization of water resources. And the second phase, it was a demonstration pilot to try to make and accessibility of technical innovation in this area, and to implement or to introduce a new technology for irrigation. The first phase, actually, we try to use the remote sensing as approach between, this study is a new project between OSS and the Regional Center for Remote Sensing of North Africa states. It's implemented in Tunisia, and in cooperation with our center, Water Research and Technology Center. The main objective, or the general objective of this study, is to use Earth observation-based technology to help in management of internationally shared aquifer, to support national user organization responsible for water resources, develop and demonstrate products responding to the need of user, integrate aquifer products with user working context and procedure, train user in use, application, and limitation of remote sensing based information, and therefore know-how transfer and cooperation with national remote sensing agency. The main products to answer for this objective We start mapping the land use and land cover mapping and change detection. Defining the objective is defining the common classification system for land use and land cover and typology of their change between two dates, for example, 1919 to 2000. The application is land use and land cover information and temporal change analysis related to water resource management. Also, we try to mapping the rainfall estimation and evapotranspiration and water balances. Donc, the objective is the use of low spatial resolution and very high temporal resolution to elaborate mapping of the rainfall estimation and evapotranspiration and water balance. The entry or the application is daily monitoring of precipitation and evapotranspiration, seasonal monitoring for water balance, and evaluation of groundwater recharge capacity. Also, we try to map the water and vegetation monitoring in the basin, use medium spatial resolution and high temporal resolution to monitoring of vegetation and large water body, and monitoring of the evolution of the biophysical parameter that describe the status of the cultivated and natural vegetation. Donc, the entry is daily and seasonal monitoring of vegetation. Also, we are mapping the digital terrain modeling and derived product. The objective is to use the radar data to create DTMS and elaborate derived products such as contour map, slope map, watershed, and sub-watershed map. The entry is to produce two products of allometric data and elaborate of watershed and sub-watershed map and flow map. Also, we are mapping the water abstraction and irrigation. Produce map showing water abstraction and annual crop irrigation consumption using the aquifer land use and land cover map. The application is identification of water over consumption and detection of illicit abstraction. Then we are mapping also the surface water body and inventory and monitoring. The objective is to employ the radar image and optical satellite image to produce water body inventory map and the time. Yes. Oh. In conclusion, the consultation and institutional benefit from using Earth observation system for shared aquifers is visibility of map data, facilitating data exchange and availability, provide transparency, facilitate the consultation of decision makers. Thank you very much for your attention.
Thank you, Badia Shelley from Water Resource and Research Technology Center, Tunisia. The next speaker is Elizabeth Guzman from the Ground Specialization Department of the Faculty of Engineering at the National Autonomous University of Mexico. She'll be sharing insights on cloud computing and remote sensing data for potential groundwater recharge estimation, and is important in water resource management in Mexico Basin. You're welcome.
Thank you very much for the invitation. It's a pleasure for me to share with you these results for the pilot project in the Basin of Mexico. I think I don't have the control. Okay, thank you. Okay. Okay, so this is the content of my presentation. I'm going right to the introduction. So understanding the potential recharge is crucial for managing groundwater resources. In the Basin of Mexico, most of the natural recharge occurs in the highlands. And this water recharge feeds the aquifer. So population settled in the basin highly depends on groundwater, extracting 2.5 times more than the natural recharge. Recharge estimations are variable and few, ranging from 36 to 172 millimeters per year. So one challenge lies on preparation and processing of data sets in a specialized software, which require users to have a specific training. And the other is the lack of information coming from stations on groundwater. So this project aims to investigate if global satellite data can be a viable alternative for estimating potential recharge in the Basin of Mexico and other areas. And in this case, can the large amount of spatiotemporal data and computational resources be addressed to recent advances in cloud computing services? This is the reference model that we use to compare with our data. It was reported by González Ortigosa last year. They used the soil water balance model from the USGS, which is a quite comprehensive software able to integrate almost all parameters involved in infiltration, such as, of course, precipitation, temperature, land cover, soil type, topography, geology, etc. The model is based on the Torway Mather model. They calculate the soil moisture at a given time t, which is a function of the previous time, and the water inputs and outputs, like rainfall, run-on, runoff, interception, etc. So they configure these four models where we can see that recharge is around 200 millimeters in the highlands to the south of the basin. And they have 0 values in red in the center of the basin. And they have low values to the north of the basin and around 1 to 10 millimeters per year. So this is the methodology that we use. We use 4 steps, basically. It consists on the first one, we calculate the moisture at field capacity and the wilting point from this open map product, which is sand, clay, and soil organic carbon content. In the second step, we eliminate the urban areas from this MODIS product. In the third step, we do a temporal resample of chirps precipitation and terranet evapotranspiration. We set them both to monthly scale. And these are input parameters for the Torway Mather model that we use, in which potential evapotranspiration is compared against precipitation. When potential evapotranspiration is greater than precipitation P, there is no recharge, but potential water loss. In the other case, if precipitation is greater than that potential evapotranspiration, water begins to accumulate, but there is no recharge because the saturation point is not reached. So this water comes for the next step. And in the next step, the saturation point is reached. So the recharge is calculated as the surplus of the precipitation. So the model is implemented in Google Earth Engine through Google Colab. It runs like any Python code, and it requires two values. One of them is the average routing depth that we obtain from this product, a 0.2. And the other value that the code needs is the initial and the final dates of interest. So these are the results of the model, the average potential recharge map for the basin of Mexico in millimeters. So we can see in this map a similar distribution compared with the reference model in the, in the southern part. This is the map of the potential recharge. In the southern part of the basin, we have values around 200 millimeters per year. In the central part and to the north, we have low values. In the left table, we can see the spatial average potential recharge for the entire basin in the first line, and for region. In the central columns, we can observe the values reported by González Ortigosa, our reference model, and in the last two columns are our values. So we obtain as an average potential recharge a value of 47 millimeters per year, compared with 45 from the reference model. A very similar value. However, when we compare or look closer to the subregions, we can observe important differences. For example, in the aquifer number 1, 2, 3, and the number 6. So now we are going to look closer to the aquifer number 1. The aquifer number 1, this is the time series in red. So we can see that the events of recharge have similar periods compared to the reference model, and we obtain an average of 151 compared with 76 of the reference model. So this is due to the routing depth that we use, which was 0.2 meters for the entire basin. Then what we do was changing the routing depth to a better value, more proper for the highlands, 2 meters in the forest areas. So we obtain a better time series, an estimate of potential recharge in average of 71 compared to 76 of the reference model. And this is the total series doing this change for the entire basin. We obtain at the end with this change in the aquifer number 1 36 millimeters per year compared with 45 of the reference model. Now the discussion is about 2 points. And at the beginning, we were expecting that the results were extremely different compared with the with the reference model, mainly because we didn't integrate runoff. So we checked the runoff for the basin of Mexico, and it turns out that is very low. As you see in the first map, the values of runoff is very close to zero. So that's why the model is working without integrating runoff. And in the second point of discussion is the arid areas. While we reduce the thickness of the soil, we try to force the model to increase the recharge, but it doesn't work. Then we didn't get a good fit of the model respect to the reference model. At the end, we obtain a potential recharge of 8 millimeters per year and against 25. So this is a limitation of the model. In arid areas, another mechanism should be considered. And our low outlook, well, since we observe a significant dependency on routine depth, we are planning to integrate this product that seems to have better routine depths for the area. Other plan that we have is look the potential evapotranspiration that seems to be overestimated on the arid areas. And the other is integrate, of course, the product of runoff, where in the areas where the runoff plays a significant role. And the last one is where we would like to try the product and see how is the potential recharge over time in areas affected, for example, by deforestation, land use, or wildfires. Okay, your conclusions is that the model is consistent with the reference model. So we need only to integrate the runoff product. That we need further investigation in arid areas. And the last one is about our experience in cloud computing services. It was easy and immediate access to results. So we think this could be a tool that may have application in water resource management. These are our references and our contact in the university. Thank you very much.
Thank you, Elizabeth. We have an online speaker, Mr. Amos Kaboba from the University of Energy and Natural Resources, Ghana. He is currently co-chair of the Program Board for Group Earth Observation, GEO, and Land Degradation Neutrality Flagship and Dean International Relations Office of the University of Energy and Resource in Ghana. He published 80 plus articles in reputable journals of the application of satellite technology for water management in Ghana and Africa. Welcome, Mr. Amos Kaboba.
Yeah, thank you very much. First, I hope you can hear me from there. Do I have to share my screen?
Mr. Amos, you have to share your screen, please.
Okay. Okay, you can see my screen.
Can you adjust it? Mr. Amos, can you hear me?
Yeah, I can hear you.
Can
I
you
just
make it?
want to be sure
Can
you
you,
can see my screen.
can you make a full of it, please? It's okay. It's okay. Proceed.
Now you can see my screen. Okay, so I hope you can hear me. So this morning in Costa Rica and afternoon where I am in Nigeria now. Greetings and thank you for the organizers for giving me the chance. So today I want to share some highlights on some work which has been done in Ghana, and this is contributed by other authors which are stated here. Now, I want to start by saying that um, there is a region in Ghana which is called the Afan Plains. This is a very important region in Ghana because it is also more like the agriculture hub of the country, but there is heavy dependence on groundwater. And you also find out that the population growth in this area is on the increase. So there has been a need to think about how can we start to look at groundwater issues in this particular area. Now, one thing you will realize in this area is that sanitation is a major problem. So you have sanitation problems, you have issues of agriculture also happening in this same region. And you also have what I call poor siting of latrines. So if you juxtapose this with your groundwater resources, it means you need to really think about issues of vulnerability. So this inspired the work that we have been trying to work on. So in trying to undertake this work, we try to adopt two methods. Now, one method is called drastic. So the drastic more or less uses the normal, let me call it AHP kind of weighting system to collect, you take different parameters and you weigh them using the AHP system. And at the end, you make a decision based on the outcome. Now, in our part of the world, getting all of these drastic parameters are always very difficult because one, you have cases whereby boreholes are drilled and pumping tests are not conducted and this information is just not available. So we try to develop a simplified model, which is called the F-Hydra model. So in this particular case, we try to look at how are the results like if you compare the two in assessing the water, the groundwater vulnerability situation. So you will see here that the results which are coming from the drastic is indicating that roughly 30% of the area is highly prone to vulnerabilities. And you also see that these areas are much closer to the water bodies. So this is what the drastic model is showing us. By the way, the drastic model is a widely used model in groundwater vulnerability. And if you Google it, you find out that quite a lot of work has been done with that. So now when we compare that to the F-Hydra, then we start to see that there is some kind of a disparity between the results. Because in the case of the drastic that is giving us 30%, the F-Hydra is giving us only 1% high vulnerability. But again, when you look at in terms of decision, looking at, for example, which areas are moderately marked in terms of the drastic, you find that the drastic is estimating roughly 50% of the area as being areas that communities or government needs to start to think about something. But when you come to the F-Hydra, it's also indicating roughly 50% chance that these areas will need to give some kind of indication as what to be done. Now, we have published this work, and if you are interested, you can look at Ajari and tell one of my students that we work together on this work. But this is work that is still ongoing. We are still collecting more data to see how to validate this work over the whole country. Those results are not ready yet, and once they are ready, we will continuously update this. But what I'm trying to emphasize in these two scenarios is that in Africa, we realize that there's a need, and especially in Ghana, there's a need to start to think about how can we sometimes simplify very complex models to simple ones that we can be able to quickly provide decisions for the people who are involved in the management of water resources, especially in this case. So in this particular one, when we had the results, so we discussed with what we call the NGOs that were involved, the African Plains Development Organization. Then we also engaged the municipal assembly, and we sat with them and said that, okay, this is what our maps are showing us, and hence there was a need for the communities to come together in order to start to provide some kind of measures in trying to safeguard and protect their water resources. So as an ongoing work, so at least this graph here is just showing the comparability between the two, which I have explained. So the disparity comes in the high side in terms of the vulnerability. And again, the weakness for the FRDRA is that, of course, we are using very limited amount of parameters in order to estimate that. So, but the point is that we are still looking at this to see how best we can still improve the results in order to provide maybe a much closer to the drastic, which is widely known. Now, as an ongoing work, we decided to go to this same place and try to adopt, in addition to what I call the potential. In this case, we try to look at what are the groundwater potential zones. It's still in this particular area. And in order to do that, first we use the AHB to do that. So we use the AHB method in order to estimate what were generally the groundwater potential zones. So you will see that generally, of course, you have a lake, so the lake areas will generally show you high potential because water is always stored there, so your recharge is always closer. But you will see that there are a lot of areas which are a bit mountainous areas, hilly areas, that are showing low possibility. Then we went further to apply a SWOT model. This is what we are still working on. We are still trying to work around this. So we apply a SWOT model to further see, for example, what are the potential recharge areas and what have you. So the need for this is to help us to understand with the vulnerabilities and with the potential recharge zones, is there a midway somewhere between drying up of boreholes or some kind of pollution, especially the fact that you have agricultural activities and also quite a number of the siting or latrines that are all sometimes not sited in a way, in a good proximity to the boreholes. So this is what we are still working on. And we hope that with the SWOT simulations, it is generally showing that, of course, the groundwater recharge is increasing. It increases just as, of course, when you have the rainfall also, because the rainfall is a main recharge, because in Ghana, we are not really doing artificial recharge. So it's all being done by rainfall. So in terms of summary, what we are trying to push forward with this work is that groundwater, because it's an unseen resource, it's a resource which is hidden from us. It requires a lot of effort, a lot of collaboration, and I'm happy to listen to the presentation from Tunisia, from all the other people who have presented. I think it presents a room for us to discuss methods, methodologies, and to share knowledge to see how continuously we can collaborate together, research on it, and based on that, share our tools, and as a result, provide a midway by which we can be able to continuously monitor this critical resource, especially in Africa, that we are heavily dependent on groundwater for water supply. So on that note, I wish to thank everyone for listening, and to all my co-authors who have also contributed to this, and to the organizers and for Costa Rica for hosting this program. Thank you very much. Looking forward to your questions.
Thank you very much. The next speaker is from Bolivia. We'll be discussing on assessing of interaction between land use change and groundwater recharge under urban heat island, remotely sensitive signature in Santa Cruz. Anne Rodriguez, please. It's your turn. Yes, online. Oh.
Good morning. It is a pleasure for me to be part of this important conference. My name is Ana Rodriguez. I am from Bolivia in South America. I am here to present the following research: assessment of interactions between land use change and groundwater recharge under urban heat island remotely sensed signatures in Santa Cruz, Bolivia. First of all, let's talk about the term urban heat island. It is used to describe an urban area that is warmer than the rural areas that surround it, and describes local scale temperature differences. The main cause of the urban heat island is urban development. Urban areas are often covered with asphalt, which prevents water underground from evaporating. Now, my first task today is to show you how I have identified urban heat island signatures using data from satellites. The next task is to show you why satellites are useful in countries with scarce resources to monitor environmental variables in cities, especially in Latin America. Then I will show you some impacts of heat in tropical cities like Santa Cruz. To begin, I have to say that last year, media has put attention on this issue because reports indicated that at least 7 people has died because of heat stroke during the month with the highest temperatures registered in Santa Cruz. But not only people was affected. High temperatures affected also livestock production. For example, poultry and swine industries have been seriously affected, facing important economic losses. Now, my question is, considering that Santa Cruz relies completely on groundwater for drinking water supply, how is drinking water supply affected? That is my research about. At this time, I will show you my concerns over a city of 1.2 million people located in central western Amazon. For this purpose, I have used data accessible to the public from the Modis Terra platform. I have used land surface temperature from year 2000 to year 2023 from an area affected by an aggressive and unplanned urbanization processes affecting the Amazonian forest. Well, one of the consequences of land use change and forest loss is the surface energy alteration balance, which in turn alters the surface and subsoil water balance. In this case, I will try to demonstrate that drinking water supply can be affected. Look at the figures in the upper part. I am comparing the imagery from year 2000 on the left with imagery from the year 2020 on the right. The two images show the dramatic impact of unplanned urbanization in a city located in the Amazonian region. The following figures show the impact of such change in land use. Comparing on the left the land surface temperatures measured by the satellite in the groundwater recharge zone affected by land use change, and on the right the land surface temperatures in the city downtown. In this case, the temperatures in downtown are much higher than temperatures in the city outskirts. Here, the differences in temperatures are between 3 degrees and 4 degrees Celsius, which is enough to make a noticeable impact. An interesting fact occurs in the case of Santa Cruz, which is that land use change is occurring in one of the areas where groundwater recharge occurs. Well, about the results, let's say that sandy soils characterize the groundwater recharge zones with high infiltration rates. Then, when urbanization processes occur, soil become more compact and in some areas land are paved, reducing or blocking infiltration and causing an increase in surface runoff. Then, together with an increase in surface temperatures, which could be translated into an increase in evaporation, sum up to more losses for groundwater recharge, hence reducing water available for drinking water supply. To express the association between all those variables, I have calculated a simple equation in representation of the soil-water balance. The results are shown in the figure in the lower part of the slide. The interpretation of the figure is simple. Above zero, positive values, the soil-water balance indicated that groundwater storage will have a gain. For the contrary, when the soil-water balance is below zero, it means that water losses by evaporation are higher than that precipitation inputs, which means that there is less water available for infiltration and, for instance, to recharge groundwater reservoirs. The first aspect to observe is that here is no clear trend, neither upwards nor downwards. That is because precipitation does not have a positive or negative trend. In other words, precipitation does not seem to increase, but it does not seem to decrease either. Considering that precipitation is the most important component of the soil-water balance, groundwater recharge does not define an upward or downward trend. However, after urbanization processes intensified in the middle 2020s, soil-water balance gets altered. Seasonal changes are more pronounced. The number of months of months with high recharge seemed to increase, but in other years, the number of months with negative soil-water balance seemed also to increase. Then, a comparison between before and after 2010 defined different recharge dynamics. Well, about the conclusion of my research, I have to say that a general definition for urban heat island identification is to find areas with considerable higher temperatures than the surrounding areas. This definition applies in Santa Cruz, where downtown temperatures can be from 3 to 4 degrees higher than in the surrounding of the city. Because of that, I can say that satellite imagery has identified an urban heat island signature for this city in the Bolivian Amazonian region. Then, since evaporation is related to temperatures, both have increased in the last decade. Data also shows that precipitation intensity has increased. In consequence, the soil-water balance behavior has changed. The approach considered here indicates that soil-water balance has intensified. Months with higher infiltration are likely to increase, and also months with less water available from groundwater recharge may also have increased. In other words, the durations are wider and peaks are higher or lower, but are much different than it was before the urbanization processes, which become more aggressive since 2010. Given that also precipitations trends have changed, questions remain, or more precisely values, to understand how the future trends of water supplies will be in the future. So, to conclude, I believe that there are many things that cities and communities can do to minimize the effect of heat islands. One of them could be for example, planting vegetation and trees, which can help increase evaporation that cools the surrounding areas. Additionally, using some new materials like cool roofs and cool pavements, and also and definitely with urban planning in order to make the cities better for the people who live there. So thank you to all of you, and I hope I have made a contribution with my research.
Thank you very much. We have a limited time, like 6 minutes. So please let us go for questions. We have 2 participants online, beginning with the first online from China, the Aman. Please, if there is any question.
Thank you so much for all the presenters. Are very interesting research. I have a question which I was discussing with Elizabeth about the situation in Mexico City. I mean, I don't know if the kind of models that she's working with can be coupled with another model that can try to estimate how much the city of Mexico is sinking. For example, one of the effects that could appear from this dramatic 2.5 ratio between the amount of water that is being consumed and the amount of water that is being infiltrating or recharging the groundwater reservoir.
Is that for Elizabeth?
Thank you. Thank you very much for the question. Yes, actually, we have in some areas a very sinking of the soil because there are some layers at the surface where we have clays. So this material can compact very fast. So in some areas we have around 30 centimeters per year of the soil compactation. And another projects have considered this compactation of the soil, and the conclusion is that the thickness of the aquifer cannot be recovered. So it's going to continue sinking or having compactation, and the storage capacity of the aquifer won't be the same in the future. So the problem now is try to reduce the pumping from wells and try to increase the capacity of the city to capture the water that is running off over the city.
Thank you. Another question for the participants from online, please. We have 2 online waiting. Proceed.
Can I?
You want to ask a question?
Yeah, I want to ask a question. This
For who? Online?
no, not online, in
Oh.
person.
Okay.
So this question, good morning, everybody. This question is for Dr. Badrian, who talked about the transboundary groundwater management in the 3 countries. And you also talked about the institutional arrangements and how it is currently working. So I was just wondering whether there have been any conflicts, because you're talking about a kind of a transboundary resource, and you also talked about a mechanism in place. So are there any examples of a conflict, and how has that been resolved, particularly with the technology that we have?
Yes, as I told in my presentation, before starting this project, the SAS between these 3 countries, and it is this 3 countries is we install platform by OSS, Observatory of Sahara Septentrional, and this platform try to share all the information between these 3 countries, common data, common research, and try to make the transfer of the technology between these 3 countries. And I think there is, at the moment, there is no problem between these 3 countries. Yes.
Thank you. Another question?
Yes, thank you. I have a question for the first speaker, Hafsa.
Okay.
Hafsa, you talk about farmer perception, gender-specific vulnerability, and also at the end about ground truth service. I wanted to know if you consider a way to spatialize this information in order to combine somehow with the different geospatial information, the different inputs you used in your vulnerability study.
Yeah, okay. So first of all, I think thanks for the wonderful question. So about the ground truth surveys that we have done with the with the farmer community. So what we have identified is if we look into the geographical locations of the farmers, where they're actually impacting most from the groundwater challenges. So actually we're trying to have a kind of discussion with them. So like how much the crop productivity in that regard is been changed from the past year, yes or no. So if their answer is giving us a yes, okay, so we start putting them in a very into a like high risk factor. And same like for the in terms of the gender like discrepancies. So when you start like the engaging with the farmer females, especially the one with the progressives, so actually we have made a kind of questionnaires specific to the locations that we are doing a kind of survey. So we're collecting the information like either how much they are actually involved in those kind of activities and how much they are engaged, and what they think that in terms of decision making where they categorize themselves. So whatever the information about this challenge we have gathered, so we actually put all those information into the certain criteria in terms of exposure and risk. And but again, geospatially, what we did, so we actually map out all those locations. We have actually did a kind of survey with the communities. So then we in the final, we come up with the kind of geographical locations. Okay, these are the areas where the farmers are highly susceptible to the kind of exposure in terms of the agriculture productivity. Okay, this is the area with the gender or the farmers we actually met with the female farmers. They are actually suffering a lot. So this is something we have been carried out. And secondly, about the ground truth survey of the groundwater. So in that way, what I did actually, we have been engaged with the different government agencies, and we are trying to get the information initially on a very manual basis. Okay, it was a kind of global method. So we actually, it was a kind of a wire, and we start putting into the ground, and whenever it touched with the water surface, then it gave us a kind of sound of sound of something. Okay, this is the water level. So this was a kind of like, initially we made a very manual effort for the groundwater table calculation. So then we made it very like automatic when we started installing the CTD divers in those areas.
Thank you very much. We have a question from Amos Kaboba online. Amos? Amos online? Not connected. Another question, if there is any, if time allows.
Thank you. Good evening. This is a question for Badia. I would like to ask her if you can explain a little bit with more detail the significance of remote sensing for water monitoring in your study area.
I think the use of Earth observation in our area can help to mapping in large area, and you can get specific maps, like I show you for the DTM and evapotranspiration. You can get also the very specific and very validate and precise data for using in this project for sharing water.
Thank you, Badia Shelley. Amos is back. Amos online?
Yeah.
You have a question? Yes. Okay, Amos, I think has lost. So what's the time now? So as we have had the session, we had a very interesting presentation. Thank you for the participants. But we have seen in the space technologies that it offers a powerful tool in monitoring groundwater resources around the world. And this has been evidently proven by the following relevance in remote sensing in geographic information system, and also in global positioning system for precise location, and also the benefit we have seen from the space technology under the water, groundwater in many resources. It covers a large area in monitoring, especially when you have a real-time data, and it is cost effective, and it is a time less consuming when you do the acquisition. Also, conclusively, I can say that the space technologies has rationalizing groundwater monitoring, which provide the variable insight for better management in water, especially in the regional level and the government level, and also the district ones. Integrating space-based data with the ground observation also had led the holistic understanding between the water managers and also the stakeholders. Though we had some gaps, everybody had discussed this concerning about the data access and quality, also the technical capacity. Most of the people seems like they don't have the technicalities to run the process, and also integration with the different data sets, like the areas, some of the areas has a different coordinate system maybe, or sometimes they don't have cause stations, the continuous one that can easily make the data acquisition, especially in the traditional method, run properly. Therefore, I can recommend maybe we have an international collaboration between the expertise, the managers, the water resource managers, the stakeholders, and other expertise concerning about the water resource management. And also capacity building, whenever happens, please let us share in order to enhance the ability on keeping this water resource sustainably. Also, the last one to conclude, but I think sometimes other countries might have the improvement in standardized portals or river protocols in the way of accessing data that can simplify the analysis as well. Therefore, when we are going to have a break, please let us have a space technology that it is better than a traditional method. Good morning.
Thank you everyone for joining. I would just like to make a short announcement. We still have training slots for the session on streamflow modeling. If anyone is interested, please let us know. And we also have 2 slots for the water quality training with the trainer being here with us. Let us know, but this is for the on-site participants. We'll do our best to record the training as well so we can make them available to some extent online later on. I also wanted to let you know that by the poster sessions, I put up some of the profile pages of stakeholders who are represented online, also some of the indigenous voices profiles with the water-related challenges. If you would like to join, then you can check out the brochure and the flyer or send me an email if you have that and let us know. And yeah, thanks a lot. Enjoy the break.
Recording stopped.
be patient for another 2 minutes. There's an echo. Mandira Shrestha from Isimod is your moderator. Mandira, the floor is yours.
Good morning, everybody. May I ask everybody outside to come in?
Recording in progress.
If I can ask everybody outside the room to come in, please. Good morning, our online participants. We're just waiting for our in-person participants to get back to the room. Yeah, so very good morning, all of you, and welcome to day 2, the second session, technical session. And I'm Mandira Singh Shrestha. I work for the International Center for Integrated Mountain Development as the Senior Water Resources Specialist and also the Coordinator of Climate Services. So this technical session, which I'm moderating, is on space technologies, monitoring flood risk and impact, and relevant climate change adaptation in agriculture. This session is for 1.5 hours. That is from 11 to 12:30. We have in total 6 presentations. 3 of them are online and 3 of them we have in person. So to start this session, we have our first speaker. He's the keynote speaker and we'll be talking about space technology for flood management. We have Rodney Martinez from the World Meteorological Organization, WMO. Rodney Martinez is the WMO representative for North America, Central America, and the Caribbean, and he's an oceanographer. He's been working for the last 30 years on El Nino as well as La Nina monitoring, predictions, and regional impacts, early warning systems, climate risk management, and related services to agriculture, water resources management, and other development sectors. So may I now request Rodney for his presentation, please. Please share your PowerPoint and kindly start your presentation. Thank you.
Thank you. Please, good afternoon. Please confirm if you have my presentation in the screen.
Yes, the presentation is there, and
Okay.
it's full screen too. Thank you, Rodney.
Okay, thank you. Good afternoon. I'm pleased to share with you this brief presentation about space technology on floods, but I would like to start by explaining about WMO. The World Meteorological Organization is an specialized agency for weather, climate, and operational hydrology, 193 member states and territories. And we are dedicated to international cooperation and coordination on the state and behavior of the Earth's atmosphere, its interaction with the lands, oceans, the weather and climate, and of course, water resources. WMO has core systems. One is the WMO Integrated Global Service System, where the space component is quite important. The WMO Integrated Processing and Prediction System, WIPS, which is the connection between the observations and the modeling and forecasting, a global, regional, and national level. And we have the WMO Information System, which is part of the telecommunication system. This system makes it possible to have this exchange of data on real-time basis across the globe. What about WMO and space-based observation? The WMO community has a long-standing collaboration with the space agencies and has been instrumental in promoting data sharing, setting common standards, and building capacity, especially in less developed countries. The WMO space program plays a crucial role in coordinating and promoting the utilization of satellite data and products to achieve maximum advantage of Earth observation satellites for all WMO applications, area and weather, climate and environmental services. And it's more, you can see the WMO space program with the different components in observations, promotion, and it's at service of all our members. And one of the important parts of the WMO space program is this OSCAR, which is the Observing System Capability Analysis and Review tool, when you can have access to all the characteristics of the satellite, the different format of data, etc. These satellites are at service of the community and as part of the system of collaboration within WMO. And Earth system observation constitute approximately 90% of data used in global numerical weather prediction and climate monitoring. They are the backbone of operations of national meteorological and hydrological services, providing invaluable insights that safeguard lives and property worldwide 24/7. When we talk about Earth observation satellites, there are 322 of the currently in orbit 32 Earth observation satellites. 23 are geostationary and 223 polar orbiting. 93 space agencies or organizations in the world operating one or more Earth observation satellites, and there is only one Earth observation satellite on highly elliptical orbit, Molniya orbit. And we have to remember that all this started in 1960 with the first world weather satellite, TIROS, was launched in April 1960. We have a lot of partners, and of course, international collaboration is a key matter with the space operator, satellite operators around the world. NASA is one of them. Here you can see the operating and future science fleet of NASA, and you have the green colors are all the satellite missions dedicated to Earth observations. You have NOAA, for example, and the current satellite missions, and the future ones that are quite operational for our work in WMO community. When we talk about floods, we have very big numbers in terms of the impact, about the frequency, about the people affected, about what is the damage each year around the world, and the trend to increase with the floods in frequency, but also in impact. Floods are the deadliest natural hazards striking numerous regions in the world each year. And WMO response to floods. We have several areas, but I would like to focus in this one: the associated program of flood management and the flash flood guidance system with global coverage. In the case of this APFM, associated program of flood management, is in partnership with Global Water Partnership. Of course, we use satellite imagery, but we work on land use management, water management, risk management is more. This is what the approach integrates. But I would like to focus now in the flash flood guidance system. And let me share this brief video with you.
While there are many different types of floods, flash floods are the most dangerous. They can strike anywhere, at any time. They are sudden and short, with a high peak discharge, and usually occur between 1 and 6 hours after an observable causal event. Every year, they claim the lives of more than 5,000 people around the world and devastate communities, economies, and the environment. In mountainous and hilly regions, flash floods can cause landslides, one of the most costly and deadly disasters.
Urban areas, water runoff is 2 to 6 times higher than on natural terrain. With 55% of the world's population urban areas today and an expected 68% by 2050, it is essential that cities around the world invest in reducing the risk of flash floods. The Flash Flood Guidance System, FFGS, has been developed as a state-of-the-art analysis and forecasting tool to address this need by providing easily accessible, quality-controlled precipitation estimates gathered from weather radar, satellites, measuring instruments, and numerical weather prediction models, the FFGS empowers hydrological and meteorological forecasters to produce timely and accurate flash flood warnings worldwide.
The FFGS offers a range of products covering diagnostic, prognostic, snow, and risk and threat related to flash floods. Special modules and components are also available to assess landslides and flash flood events in urban areas.
The FFGS will work to enhance the capacity of NMHSs, mitigate the adverse impacts of hydrometeorological hazards, encourage collaborations with disaster management agencies, foster national and regional developments and collaborations. Since its implementation, more than 400 meteorological and hydrological forecasters have received extensive FFGS training from the World Meteorological Organization and project partners, and more than 50% of the countries involved now have access for the first time to real-time products that enable them to issue timely and accurate flash flood warnings, make efficient assessments, and rapidly mobilize response teams.
By the end of 2019, FFGS covers more than 60 countries and 3 billion people. Because flash floods often cross national boundaries, regional FFGS projects and cooperation are essential. With the frequency and severity of flash floods only expected to increase, the development and implementation of the FFGS is more crucial than ever to protect communities, safeguard economies, and save others' lives.
Join us.
Well, and to continue the presentation, there are several resources available. I think it's a challenge to cover all of in this very short time, but I would like to reference the mapping portal of NASA, for example, products on near real time for floods, which is increasing, and there are new ones there. Also, what is provided by the JAXA, the Japanese Space Agency for Global Rainfall Watch, that enables to obtain information in different ways about the precipitation. We have also the emergency management service from Copernicus, when you can also get information about flood monitoring in real time and data, of course, for research and operational purposes. In the series of GOES, our satellites, we have several modalities, but one very interesting is rainfall rate quantitative precipitation estimation. And there is also application, like, for example, this one from the University of Costa Rica, in terms of lightning and storm. And you can, with this, have a better idea of where the convective systems are moving. And we have also some products, new products available from the Argentinian satellite, SAOCOM, which is, it was proved in the emergency with Otis this year. This is a very schematic flood monitoring diagram, when you can see all the value chain between the data collection, analysis, flood extent monitoring, but also with the input of modeling and prediction, model validation to generate products, training, services to users, and the end, trigger flood response. There are many products available. There are many simulations that have been proved to be effective in pre-flood and now casting satellite products based in the information of satellite-based soil moisture monitoring, and also satellite-based precipitation and soil water products. There are many of them available. We have also flood monitoring capabilities from satellites in terms of real time in different through synthetic aperture radar flood mapping, for example, or optical flood mapping, which is also available. And with flood modeling, we have several models, but I would like to mention that currently the only satellite data utilized in flood models is from the radiances and winds assimilated into numerical weather prediction models, which are then used to model precipitation used by flood models. GLOFAST is a model that is being more frequently used to provide downstream countries with information of upstream river conditions, etc. So now it's possible, and there are also many excellent initiatives when tying satellite data and socioeconomic information together. one important initiative, which is very useful and has been applied here in the region, is the GeoGLOS, which is the Global Earth Observations Global Water Sustainability Initiative, which is based on modeling, of course, of hydrological estimations for a lot of rivers in the world. And this is combined with satellite imagery. And in the end, you can have this kind of access through the portal and make applications at national level. We have had a very nice experience in integrated river and flood forecasting system in Dominican Republic. This is the scheme of how this integration has taken place. And we have also the application of GeoGLOS in national risk management system in Ecuador, when most of the hydrological services are provided through GeoGLOS in combination with the local stations. I would like also to mention the long-lasting efforts in terms of capacity building. We have the BLAB as a global network of training providers in satellite meteorology and related fields. WMO and the Coordination Group of Meteorological Satellites established the virtual laboratory for training and education in satellite meteorology in 2000. And we have now around the globe 13 specialized training centers and 8 satellite operators working together to improve the utilization of data and products from meteorological and environmental satellites. Costa Rica is one of these nodes with the University of Costa Rica, which is also part of the regional training center of WMO. And we have also the Earth Observation Training Education Capacity Development Network, which aims to improve collaboration among the Earth observing capacity building providers, foster exchange of capacity building resources, and reduce duplication of efforts. So there's a strong coordination efforts, and the thematic focus is on disaster risk reduction and climate adaptation and mitigation. But despite of all these efforts, despite of all this available information, we still have the impact of severe floods. And this is just to take this opportunity to express my solidarity with the Brazilian people for what is happening now in Rio Grande do Sul in Brazil, when we have a severe impact of flooding in this region, with dead people, with a lot of impacts in most of the state in Brazil. So we need to do more. And finally, final remarks is satellite community is one of the most pragmatic examples of successful international cooperation around the globe. This is collaboration. Currently, there's open access to a vast amount of satellite data and information that can make a significant difference on flood early warning and management. However, more efforts needs to be done to expand the utilization of this data and information at national level and trigger an early response and actions in the field, in the ground. We really need to increase our efforts to extend this community of practice. We need to provide more training. We need to have more people involved to leverage these available resources to save lives and mitigate further impacts. Thank you very much for your attention.
There you go. No worries. Well, thank you very much, Rodney, for your very informative presentation. If there are any questions from the floor, we still have some time. 1 or 2 questions we can take, or from our online participants regarding the overview that he has provided on WMO activities and also early warning systems. So is there any question online? No, so there are no questions online either. So I have one question for you, Rodney. The question is like, there are so many abundant and increasing accurate satellite data and information to improve water management, in particular flood risk management in Latin America and the Caribbean regions. Well, you did say that there is much more needs to be done, but what is needed to foster this application, its application more in the region? You know, there are data, there's information now, there is also products, there's models, there's tools, but what needs to be done to foster application? Can you please respond to this question?
Yes, thank you for the question. I think it's important to increase our efforts to connect the scientific and operational community, which is expert on managing this data and information, but now it's still there. It's a small community processing this information, but it is not going through the decision makers. So we need to strengthen the connection with the decision makers and the institutions that can apply this information for risk management and an early response. That is the main problem, and also is a very reduced community in the region. So we need to provide training and involve more experts, more young scientists, more people in the use of the satellite information, because I think there's an over offer. It's an abundant offer of information which is not being used to solve the problems in the ground. So I think that is the challenge, that we need to work together on this.
Well, thank you very much, Rodney. Let's give him a round of applause, please. So now we have our second speaker today, and she will be speaking about identifying annually flood-prone areas to aid communities in developing improved agricultural practices. And we have our speaker, Ana Miriam. So Ana Miriam Villalobos Velasquez, she works for the Ministry of Environment in El Salvador, as a professional in remote sensing applied to risk management at the Threat Observatory, with applications in flood mapping, in landslides, in forest fires, and forest mapping. So let us welcome Anna for her presentation. You have 12 minutes and leaving some time for questions.
Hello, everyone. My name is Miriam Villalobos. I am from El Salvador, and I work in the Ministry of Environment and Natural Resources. Today, I have the pleasure to present to you some applications of space technology for flood risks and its impact in agriculture. The title of this work is Identifying Annually Flood-Prone Areas to Aid Communities in Developing Improved Agricultural Practice. The goal of this work is to identify flood areas and the periods of their occurrence to support the creation of strategies that improve crop management and reduce future losses and damage in those areas. In the image in the slide, you can see some crops flooded by Tropical Storm Julia in 2022. In this presentation, I will cover an introduction, the methodology applied, the results obtained, and the outlook and the future things to do, and finally, some conclusions. In the introduction slide, I want to show you the flooding hazard in El Salvador. El Salvador is a small country located in Central America, and we have two seasons, the rainy season and the dry season, and the duration of this season is almost 5 months. But during the rainy season, we are affected by tropical cyclones from the Pacific and the Atlantic basin. And these events generate floods that we are categorized as urban flooding, flash flooding, overflows of flows of main rivers, and waterlogging. But what happened? When an rainy event occurs, many of these categorized of flood are reported, except waterlogging. Why? It is because it's not possible to visit this place during the rainy event. or the people think that the floods are normal because they see every year. Okay, for that, we underestimate the losses and impacts in agriculture. And to support this, we need to apply space technology for map this area. Regarding to the methodology applied, we use change detection with satellite data from SAR and optical images to identify the impacted crops area under intense rainy conditions in two aspects. The first one is for flood mapping, and the second one is to identify a seasonal variation of water bodies. One of the most important results that we obtain is the area with high frequency of flooding. These areas were identified using Sentinel-1 images for tropical cyclones that occurred between 2018 to 2020. These areas are 8. If you see the map, if you see this map, you can see 8 areas, and many of these areas are located in crop field close to the coastal zone of the country. Regarding to the optical images, we use normalized difference water indices just in the image when we don't have clouds. Normally, it's happened after the rainy period. Another important result using Sentinel-1 is the identification of direction of flooding in one region. The study case that I show you is the tropical storm Amanda on 2020. If the duration of these floods is an important parameter for the impact-based forecasting to the Hydrological Forecasting Center in my institutions. If you see this example, you can see some areas have a direction of more than 20 days. Another example, but in this case, we use Sentinel-2. These are optical images. The study case is the low basin river of Rio Grande de San Miguel. And because in 2022, the tropical storm Julia affected the areas close to the river called Rio Grande de San Miguel. These floods generate affectation of the crops field. If you see the graph in the slide, also you can see which land use were affected by this tropical storm. Many of these are basic grains, sugar, and other crops. Considering to the previous cases, the space technologies for flood mapping allows to identify affected areas. These areas normally are not accessible or are disconnected. And these areas are important also to validate the flood modeling purpose. Also, we can identify the losses or damage on crops and identify recurrence and provide tools to propose solutions. In the picture, you can see some crops flooded by the tropical storm Julia in 2022. The second aspect that I mentioned before is the use of space technology to identify seasonal variation of water body. Why is important? Because we have some case that the people do agriculture in these areas. And this is that the case is the fluctuating land area in the upper part of Cerro Grande wetland. This is the bigger reservoir in the country. If you see this image, you can see the number 1 area. This is the Cerro Grande wetland. So these fluctuating land areas correspond to the banks of the reservoir that are exposed during the dry season. But these lands are very important because this area have high productivity value due to the degree of the fertility and the humidity. To map these areas, we processed Sentinel-2 images from 2018 to 2023, and we found the area is more than 3,800 hectares. But I want to mention also an example of the floods occur in this area. In 2022, during the dry season, when the people cultivate, a flood occurred and generate losses in crops. Considering the same study case in the wetland Cerro Grande, our study says that the farmers and the artisanal fishermen in the area are affected by soil and water pollution, and also the proliferation of pests and diseases and hyacinth of water. Regarding to the hyacinth of water, you can see in the pictures the hyacinth of water on 2019 in this wetland. And we obtain the percentage of area covered by hyacinth of water, and the percentage is more than 50% of the total water body. You can see the figure to the right. Okay, in the next slides, I want to show you some applications that my institution, the Ministry of Environment, is working on for different users. The first one is the data cube. This data cube is a platform. It allows integrate several data sources like MODIS, Landsat, Sentinel-2, coverage map generated by Rapid Eye, and LiDAR and historical aerial images. This data cube have many applications, but I want to mention some applications. I want to mention the applications related with the water management. Assessment of the tree cover loss, increase and reduction of water meter bodies, and the water quality assessment. The second applications is the use of the artificial intelligence to communicate with agriculture sector's users. This application is called Chateau. Chateau is a chatbot that allows to consult many information on different hazards like earthquakes, landslide, and the weather, of course. The information available in this chatbot is the precipitation, wind speed, temperature from yesterday, today, tomorrow, and the next week. Also, there are information of climate outlook, impact-based monitoring, forecasting, special reports of the different hazards. Okay, and the outlook and the future things to do. I enumerate 3 things that we need to do in the future. The first one is the implementation of El Salvador Data Cube to support efficient analysis applied to the water management. The second one, disclosure of information to interested parties, population affected, different levels maker decision makers, sorry. And the last one is incorporate climatological information and show how to interpret enclosed issues. Finally, the conclusion, special technology applies support the estimation of impacts, damage, and losses, especially in crop areas, due to the occurrence of extreme events that influence the country. And integrate analysis with climate and economic data needs to be performed in order to provide responsible estimation of losses. Artificial intelligence applied in chatbots to improve the communication with users grouped in the agricultural sector constitutes a tool that improves the early warning system and maintains that sharing of information to support decision-making process, reduce losses or damage, and guarantee food sustainability. Thank you very much for your attention.
Thank you very much, Anna, for a very nice presentation and being on time. We open the floor for 2 questions online, if you have any, and as well as for our participants here in person. Yes, we have one question there. Please introduce yourself and then the question, please.
Hi, I'm Jorge. Thank you for the presentation and the tools that you showed us. It's an amazing job. So congrats on that. I wanted to ask a little bit on the quantification of losses and damages on crops that you mentioned. If there is something already, like if you can give a couple of details about that, or if that's something that would be enhanced later on. And the other thing is, where is all this processing taking place? Like, is that in a software, in a platform, or where is that being conducted? Thank you.
Okay, thank you for the questions. Regarding to the damage or losses in the field crops, I don't know exactly because my analysis is just this is the area affected. This is the crop affected. But the people need to know how can they do. But in my case, my limitation is just to show the map. And the second one is I started to use the new platform of Copernicus that I don't remember exactly the name, but it's the new platform. They're using an API process, and it's easy to use because you can choose the area and the time, and you can download or process the information in a few minutes.
Hello. ¿A dónde se puede accesar a Chato?
Version license side of the chat or the website.
Yes, the Chato web is in the web page of the ministry. If you, I don't know how to share the link, but if you write in the Google Chrome, you can write MARN, it is the name of my institution, and the Chato is the first thing that you can see.
MARN is the Ministry of Environment?
Yes,
MARN.
yes. In the main page, the Chato is there.
Okay. Is Chato based on ChatGPT or similar?
No, I didn't work with the performing the Chateau, but it's another kind of artificial intelligence. It's not ChatGPT, but it's similar because the information is only for the observatory information, natural hazard reporting, especially informs.
Can Chato deliver information to mobile phones?
Yes, of course.
Via WhatsApp or by email, I don't know.
At this moment, just in the website.
Okay, perfect. Thank you very much.
You're welcome. Sorry.
Thank you very much. Let's give a round of applause to Anna, please. Now we have our third presentation. Our third presentation is on flood modeling of the Cagayan de Oro watersheds. And this is from the Philippines. And giving this presentation, we have Faye Ociones. And Ms. Faye Ociones is an environmentalist. And she's worked on research for the Philippines government. Her research is primarily on watershed management and vulnerability and risk assessments to inform policy as well as decision making. So Faye, you have 12 minutes.
Okay, good morning. My study is in flood modeling of 5 watersheds in Cagayan de Oro City using terrain analysis. So in the Philippines, about more than 60% of our land area is located in the mountainous regions, no, or the uplands. So usually our big cities are located in big valley plains, which are really very vulnerable to flooding. So the study really aims to determine the cause of flooding in these major cities in the Philippines. So Cagayan de Oro City is one of those major cities that we have. So next slide, please. So Cagayan de Oro, as I have said, is located in a large valley plain. That's the location. No, so I used terrain analysis, and this involved the geomorphological and spatial assessment of the watershed in terms of watershed shape and relief features and channel morphology. Particularly, hydrological parameters used include circulatory ratio for watershed shape, and the bifurcation ratios, stream densities and frequencies, and relief ratios. So that's also the parameter that was used by Dr. Dietrich Schroeder of the University of Applied Sciences in Stuttgart, Germany. So that's the same parameters that he used in analyzing for terrain analysis in the watersheds. Next slide. So these are the 5 watersheds. This is the drainage map of the 5 watersheds. This is the Iponan watershed, Cagayan de Oro, the Bigaan, and the other are Umalag and Liponan watershed. So as you can see, this is the drainage pattern. In watershed, this pattern is called the dendritic pattern of water drainage pattern, no? Dendritic. Actually, dendritic pattern of watersheds indicates that the high erodibility of the soil, no? The dendritic pattern. So we delineated this one from the 10-meter interval topographic map, which is a higher resolution topographic map. So we delineated this one. And for getting the bifurcation ratio, we had to do a stream ordering. So we used the Strahler and Horton method of stream ordering, which if you have two first order streams meeting, so the next order stream would be 2. And if you have 2 stream order meeting, that the next stream order would be 3, and so on and so forth. So the result of the terrain analysis shows that there are 2 watersheds that are highly vulnerable to flooding. This one is the Cagayan de Oro and the Iponan. So I want to concentrate or more detail on these 2 watersheds. Next slide, please. So this is the Iponan watershed. It is a 6th order stream. The land area is about 47 plus hectares, considered as a medium-sized watershed. So in terms of usually, we analyze for drainage density. Drainage density is the number of streams, the number of streams in a given area over its area. And the stream frequency is the length of all the streams over the area. So if you have high values for this one, that means that they would have higher peak flows, or they're vulnerable to flash flooding. And bifurcation ratios is the ratio of the number of streams of a given stream order compared to the next stream order, the number of streams. So again, the lower values would mean that it's vulnerable to flash flooding. For circulatory ratios, the ratio is up to 1, which means that it's a perfect circle. Of course, in reality, there is no perfect circular watershed, but circular watersheds, no, let's say it's a 0.8 or 0.7, that is a high value. So it's really prone to flash flooding, because in circular watersheds, water from remote area in the watersheds would arrive at the main channels all at the same time. So it's vulnerable to flash flooding as compared to elongated watershed, where the water have already drained down before the water from the remote sites would arrive in the deposition zones. So in terms of circulatory and bifurcation ratio, Iponan watersheds is highly vulnerable to flooding. No? And we looked into the activity upstream. The picture here, as you can see, sedimentation is high. And this is an upstream river system. No? Because what they do there is they extract the boulders and the stone in the river, crushed it for gravel. So this changes the geomorphology of the river system. And these stones are actually, they serve as a deterrent to the high velocity of water. No? So they changed that. As you can see in the remote, in the imagery on the right side, so in the ocean, in the ocean, you can see the high sedimentation that's occurring downstream because of this activity. So we really recommend, because flooding would be aggravated, no, if you get the stones or the boulders up the river systems, especially in the upstream and the midstream. So we recommended that this activity should be regulated or banned totally. Okay, so next slide. This one is Cagayan de Oro River. So it's 130,000 hectares, considered as a large watershed. So it's the same with Ipono River. Bifurcation and circulatory ratios are also the cause of high flooding in Cagayan de Oro River. Cagayan de Oro River. And the upstream portion comes from really high mountains in the area. We call those mountains Mount Kitanglad and Mount Hinatungan. So they are about 2,000 meters above sea level for Mount Kitanglad and 1,700 meters for Mount Hinatungan. So these have high or steep slopes. No? The Iponan River is the Iponan watershed is also vulnerable to pollution, actually, because this locates the landfill of Cagayan de Oro River. So, and also they have gold mining upstream. So for for mercury and copper, and also what do you call this? Other hard metals, they are high in this watershed Iponan. So next slide, please. So we mapped out in the deposition zone. The left side is the Iponan River. So the red areas are the 1 to 5 meters above sea level elevations, and the blue, the 5 to 10. So these are vulnerable, no, to flooding. So we recommended that these areas be buffered. The span of the buffering in the river should be longer, no? Because in the Philippines, we based our river buffering on land use, no? So for urban areas, it's 3 meters, for agricultural, 20 meters, and for forested areas, 40 meters. So we recommended that they should not base buffering of rivers based on land use, but it should be based on the terrain, terrain and its vulnerability to flooding. So for the deposition zones, for critical watersheds to flooding, it should be not only 3 meters. No, it should be from 5 to 10. Okay, so next slide, please. So we also recommended the land classification, the green app is recommended to be forested. This is the 18% and above slopes. For soil and water conservation, they should be forested. And the yellow is the alienable and disposable land classification. But as you can see in the existing land use map that was classified using the ALOS imagery, already there is agricultural and grassland have changed these forested areas. So this is one that have aggravated flooding that is occurring in those areas. Next slide. So we also recommended that the critical areas in the river systems like the river terrace, the deltas and islets, no, they should not be, the land use should not be for urban or for built-up areas. That should be reversed for protected areas. Because in 2011, our whole barangay, which it was in a river terrace, the population was more than 3,000 during a very strong typhoon that occurred at night. The whole barangay was washed away, so the mortality rate was really very high. So next. So aside from buffering, I've already mentioned that a while ago. So reforestation should be implemented in the river banks and also for steeply sloping areas. Next. So I've already mentioned that. So next. So you should render critical areas as protected areas and no-build zones, and to increase buffer zone areas. I've already mentioned that. So regulation when it comes to land use changes, especially in the upland areas. Next. So thank you very much for listening.
Thank you very much, Lei. There's room for one question, real quick question, if there is any. I don't see any. Is there an online question? No, I see no question there. So let's go on and thank Dr. Lei. We go on to the next presentation, and our next presentation is leveraging multi-satellite remote sensing data and machine learning for flood risk assessment in Namnoga River Basin. And this is from Lao PDR. And making this presentation, we have Sak Davong Mangeshan. He is at present with the QC Institute of Technology in Japan. Let me just give him a quick introduction of his. He's a university lecturer at the Electronics and Telecommunication Department, Faculty of Engineering, National University of Laos. So in addition, he's also the national point of contact of the Space Generation Advisory Council from Laos. So he's been promoting this space technology in a number of locations, including for education, for schools and universities. So let me now welcome Sak Davong Mangeshan for his presentation. If you would kindly please load your presentation and start. You have 12 minutes. Thank you.
Hi, my name is Sak Davong Mangeshan. I am a PhD candidate at Kyushu Institute of Technology in Japan, My presentation today is leveraging machine learning and open source satellite observation data to access the flood risk in Nam Ngum River Basin in Lao PDR. So this is the contents. So we have the overview introduction, we have objective of the research, we have methodology, result, and conclusions. So let me keep briefly about overviews water resources in Lao PDR. If you can see the maps, Lao PDR is landlocked in Southeast Asia with the total area about 236,800 square kilometer. So our population now is 7.7 million in 2024. In 90% of the country, territory is located in the Mekong River. So the monthly river flow by the patterns of the rainfall is around 80% in flood season during the rainy season and 20% drought season in the dry season. So Lao Vida is a landlocked country, but we have abundant of water resources, which there are total 62 river basins from the small basin area to the large basin area. So our introduction, we would say that flood is one of the most frequent and damaging natural disasters that have damaging the human life, poverty, infrastructure, environment, and socio-economic losses. So you can see this when the river bank is overstocked, the water overflow to the floodplain, posing a danger to the society and community. So this is a case study in Nam Ngum River that we have affected from the riverbank overflow. So the frequency and severity of the floods are expected to increase due to the deforestation, human activity, and global climate change. So our research aim and objectives: first, we want to predict the flood subsidy model as well as the risk assessments based on open source satellite remote sensing data, GIS, and machine learning, and to analyze its possible effect on the different land use land cover classes population, to find out the accuracy flood susceptibility zone in Nam Ngum River Basin, and classify the whole basin area to the flood classes starting from very low to very high. To evaluate the compared towards other machine learning, so we selected the three machine learning algorithms. So we have artificial neural network, random forest, and support with the machine. Also, our research will be contribution to the national strategy on disaster reduction, especially for the Sendai framework for disaster reduction from 2015-2030. And also this research can promote alignments with the objective of sustainable development goals, especially for SDG 11, sustainable city and community, and also SDG 13, climate change. So our study area, if you can see in the geographics, like Nam Ngum River Basin cover 16,906 square kilometer with the elevation ranging from 2,569 meters above to the sea level. So this have floods happening in 2018. So we can get this from the social media and also from the news. So the river length is approximately about 472 square kilometer, covering to 19 development districts, spanning about 6 provinces, and also represent 2% of the total area of the Mekong River basins. However, the Nam Ngum River basin had many issues, such as like we have water is used for various purposes. We also have hydropower developments. Irrigation scheme have increasing development throughout the basin. We also lacking of sub-basin management plan, and also impacting water-related disasters like flood and droughts. So for our methodology, we use like historical data from Sentinel-1. We also have floods inventory data. We have total like flood location 388 and also non-flood 388. So 0 is represented in no floods and 1 is represented in floods. We also have create the condition factor. Total we have the 11 condition factor. So we also use the Aulo Pasa drain, the light parameter for fast condition factor. We also had features suitable tests. We split 70% for training and 30% for testing. So we also use a machine learning model to do comparison, and we also have like model validation using area under the curve of receiver operating characteristic, and also we use we get the land cover effect for to the population and also to the land cover. So this our results. In our result, we have like we use a feature selection and evaluation using the, for example, variant efficient factor. We also have tolerance, and also we have pressure correlation, and also information gain ratio. If you can see this one in the information gain ratio, slope and elevation emerge in high influential with the value 0.49. However, like rainfall, distance to river, and curvature aspect being very less information factor. The multicollinearity test showing the slope had the highest variant inflation factor, following by topographic witness index. However, we can see no significant collinearity was observed among the selection flood condition factor. And patient collection of efficiency clarify slope and elevation emerge a pivotal. So our result for machine learning. So based on RUROC, if you can see in the graphs, random forest demonstrated superior performance over the SVM and NN, and also the random forest and SVM showing the highest accuracy by following by the NN and with the 91% accuracy. Likewise, the random forest and SVM exhibited the highest F1 score also, about 95%. So the mean square error and root mean square error, the random forests are the lowest, exhibited the best performance. So in our result, we would say random forest is outperformed than SVM and NN. So this result for the fast substitutability. If you can see from very high, we can see the NNs showing the highest percentage for 44%, and the high facility map, we can see that SVM is a high percentage, about 12%, and also moderate, we can see the random forest is showing the highest percentage, about 18%, and low subsidy area, we can see both like random forest and SVM had high percentage subsidibility area, and very low, we can see random forest is also high percentage subsidibility area. So in this result, we can show the effect of population and effect of land use land cover. From the analysis, we can observe the number of people vulnerable to the flooding ranging from the 650,000 people to 685,000 people, which is 85 to 90% of the population. So you can see in the right in this figure. And also effects land use land cover change. The high and very high subsidy area are agriculture, petty, orchards, and built-up area, clearly showing the flood's high probability affecting activity of the people there also. So in this one, we're showing the land use land cover and also the population. So in this the population area lying downstream of the Namgum River, you can see in this one, is the major settlement are highly vulnerable to flooding, and the upstream of the Namgum River reservoir, for example in Wang Vieng and also Back District, and also vulnerable to flooding.
You have 1 more minute, please. Please kindly wrap up.
So in our conclusion, we want to conclude like Lendong Forest is outperformed than SVM and NN, exceeding the high accuracy based on the receiving operating characteristic, and also slope and elevation remains a key factor affecting fast occurrence, with the low lie area being more susceptible due to the water accumulation, and possibly 85 to 90% of the people are highly vulnerable to flooding within 260 to 280 square kilometers of the built-up area. Lastly, the study underscored the significance of informed decision-making in disaster reduction, urban planning, community preparedness, emphasizing the important aggressive flood forecasting model, and also advanced warning system guiding by the critical information factor and identifying in this research. So thank you for your attention. So this is my contact detail and my email. You can contact me if you have any doubts and also want any information about Namgum River basins. Thank you so much.
Thank you very much, Mr. Savalon. We do have, time for one question. If there's any question from the audience here or online, please. Well, isn't? All right. So we move on. This was a presentation that was recorded, I understand. So we move on to the next presentation. It was an interesting presentation indeed, talking about the application of machine learning and AI technology, which is coming up quite fast in terms of its applications. There are, of course, many areas where better understanding needs to be made. So let's move on to the next presentation, which is also online. And this presentation is on satellite-based framework for comprehensive assessment of crop loss in flood-affected regions. This is from the Sindh flood 2022 in Pakistan. And making this presentation, we have Professor Sawaid Abbas. Professor Sawaid Abbas, he's working at a Smart Sensing for Climate and Development GIS Center at the University of Punjab, the Center for Geographical Information, University of Punjab. He's a spatial data scientist who works at the nexus of earth science, ecology, and climate change through leveraging remote sensing, machine learning, and strong domain knowledge. His key work involves forest succession, drought, and rangelands, which were accomplished through collaboration with many different institutions, which includes WWF, also ICIMOD and ICRAF, AFCD, and KFBG, all these acronyms I'm sure some of you may be knowing. But let us now welcome Professor Abbas. So Professor Abbas, please kindly have your presentation loaded, and you have a total of 12 minutes. Thank you. Professor Abbas, can you hear us?
Hello. Hello,
Yes.
thank you very much. So will you play my presentation? I shall play by myself.
You please upload your presentation so you have the control. And then, yes. We do not see a presentation yet, Professor Bas.
Yeah, just let me share screen. Okay. Yeah.
Okay, yes, it's there.
Okay.
Please go ahead. You have 12 minutes.
Okay. So thank you very much, and sorry for this little bit interruption. Okay, my talk is about development of a rapid framework for comprehensive assessment of crop losses in a flood-affected region. So there was a severe flood in August 2022 in Pakistan, in Sindh province, which is in the south of Pakistan. And since there was a flood, and we have to look for, as a developing nation and some other part of the world, for loss and damage fund. So for my colleagues with EC Dr. Faisal and other friends from other institutions, so we develop a consortium to develop a rapid methodology to understand what are the losses actually, and what we can ask for the aid, and to help us, also to help the affected people, and to cover up the losses. So this was actually to plan to use the satellite technologies to understand how much we have lost and what are the losses to the cropland, especially in this region. So this is the overall objective of our study. We used pre and post-flood images. I think this is a very state-of-the-art framework for such kind of a studies, and I am thankful for our previous presenters. They have a detailed description on how we can use these kind of technologies and the methods for flood mapping. Okay, let me a little bit explain about my study area. So you can see this is about at the end of around Pakistan, in the south of Pakistan, the Sindh province, and it is like one of the biggest provinces, one of the five provinces in Pakistan, and then the one thing we need to note that its mean annual rainfall is about 150 to 180 mm generally, and most of this rainfall happened fall in July and September. But in August 2022, so you can see the total rainfall, like it exceeded at some station. It was recorded only in August, like 1200 mm. You can understand it is almost at some places 10 times higher, and in Balochistan province it was 6 times higher rainfall as recorded previously, and then in the Sindh province it was 7 times higher the rainfall with respect to historical averages. So it was a lot of rainfall, like heavy rain shower. So we look up into the about the rainfall dynamics, and then to understand, okay, from the station data, we may not have a complete picture of our overall spatial distribution of the rainfall. And then we use a GPM, Global Precipitation Measurement Mission, to understand the spatial pattern of the rainfall. So here you can see the dark blue patches in the south part of Pakistan, southeastern part, which indicates that the heavy rainfall, which are around more than 800 mm to around 1000 mm. So this was a region which was mostly affected by these rainfalls. Okay, so the rainfall is one phenomenon, and then the another part is waterlog or the water inundation area. So for this, we use the Sentinel-1 images, which are synthetic aperture radar. Our previous presenter also explained it very beautifully how they can use this technology. So we just use those pre and post flood images to map the extent of the flood. So this was our second task, and then we realized like around 1/5 of the total study area was waterlogged. In this, we can see that, like in this region, the northwest of Sindh province are northeast of the Balochistan province. They were waterlogged area over here, and then the situation was further unfortunately exacerbated by the heavy discharge from the barrage very next to it, the Sakhar Kudu barrage, and then there was hail torrents from the neighboring hills in this region, Kirthar mountain range, and then it caused a lot of flooding over this region, like in this part of the state area. Okay, then just to emphasize what has happened over, there was numerous news stories, and then like you can see CNN how they reported it like 100-kilometer wide inland lake. So this flooding has caused, like from satellite images, so you can see this on the middle image, the 31st August, it formed like an inland lake. So that was, and then waterlogged for a very long period of time. So these are some another insets where we can see the red, the blue area is indicating the flooding. Okay, the flooded, then we, based on those flood water extent map, we calculated the, as our aim was for response action, and then to help those affected communities and to raise some awareness. So we calculated at district level how much district, like you can see that most of the district, like more than 50% of their districts are completely underwater. Okay, then the next step was to calculate the impact on the cropland, and for this we use the LDVI image. This was also from the satellite remote sensing. Primarily, it is an NDVI, normalized difference vegetation index, which indicate about the vegetation health. So we took the difference of pre and post flood images, and then we can plot. You can see in the image C in the top right corner, which indicate the difference. Here the red areas are indicating where we have a significant crop losses. Technically, it is vegetation losses, but we know that there is mostly these are crop area losses. There are mostly crops in this area, so we can say that this is like the change in the greenness value of the crops. Okay, so then you can see this in the top left corner. There is a big one red patch, and one red patch is over here. I will explain it in the coming slide. Okay, so then to understand which crops has been affected and in this region. So we had a rice production like map, and then the three major crop: rice, sugarcane, and cotton. So we can see that in this part of in the first image, top left corner, we can see this is mostly rice crop over this region, and then in the middle is the cotton and the sugarcane crop. So which means that mostly affected was the rice crop because the overlay. Then based on this, you can see that the sale-wise, this is another sub-district level region. We also calculate the crop area, and then how much is the damage to cropland in those sub-district level, and then we evaluate the percentage losses to cropland in those areas. So we evaluate like rice, cotton, and sugarcane. They lost around 80%, and then 61% of their overall loss in the crop. And then which actually cost us around $1.3 billion. Apart from these three major crops, there were this region is also known for other vegetable crops like tomatoes, onion, and chili, and they also contributed to around $374 million. And I know at that time when there was a flood, so we had like spike in the prices of tomatoes and these onions. So if in a overall scenario, if we I conclude, I think this was made by the CMOD's team. This very good illustration. That summarizes of whole study. Total national average of the like 243% higher annual rainfall in August 2022. And then in Balochistan, we have around 600% more rainfall, and then in Sindh, around 700% rainfall, and around 14.5 million affected people in the Sindh province. And this whole overall in 33 million people were affected across Pakistan. And then when we calculated the losses to crops, and we then converted into like evaluate how much has been lost, like 4.9 million hectares of cropland area were lost, were like somewhat affected. The total area of cropland was around 5 million hectares, and out of which more than 50%, like 2.8 million hectares of the cropland were affected. And then if we evaluate the production losses for the rice, it was 1.9 million tons, and then which cost around 453 million US dollars. And similarly, sugarcane for 485 million, cotton 485 million, and then sugarcane around 273 million US dollars. Apart from that, we have other losses for livestock losses of 313 million US dollars. So overall, like we try to integrate space technology and then the impact of flood to convert those losses and to estimate actually into loss and damage, to build some statements over loss and damage due to these flooding in that Sindh province. And we are really looking forward to transform this exercise, actually a framework, into a more dynamic system, which can automatically evaluate when such event can happen. Okay, so we have already published this work. I know this is a very short talk. One report is published by ECMOD, and then we also published this work as a research article in scientific reports. So I think I should actually make a QR code for this for the audience if they can scan it. I'm sorry for that. Thank you very much for listening very patiently.
Thank you very much, Mr. Abbas, for this very nice and concise presentation. I think you've covered quite a lot with the framework as well as the examples of collaboration across institutions in coming up with very timely products, particularly crop estimation. I recall Dr. Faisal, actually, he's a colleague of mine that you referred to, that you worked with. So we can take one question if there is any from the audience here or online. Is there any question that we have? Any burning question? I don't see any. So thank you again, Dr. Abbas, and a round of applause for him, please, again.
Thank you very much.
Yeah, so now we proceed. Yes, Nina? Nina has one question. Actually, I was conscious of time and going quite quickly, but let me give Nina the floor here for one question.
I'm sorry for the interruption, but I would be curious to learn how easily can we apply this framework, as I would call it now, to other regions in the world? And is there any training material available on how others can use this? Because I think we have increasingly many areas being affected from such floods, and given the food security questions that also arise, this could be very useful.
Thank you very much, Nina, for a very actually interesting question. I think that's why we have published a scientific paper also, which is explaining the methodology, which is very straightforward. May not be for a layman, but for a little bit of knowledge of remote sensing analyst or GIS analyst, I think they can easily implement it. There is almost all these data sets which we have used, they are open source and they are available, except from the local knowledge about the economic cost or the what kind of a crop area is there. So if we can we just need that from the local knowledge. Otherwise, all that processes are there automated, and they are actually well-established methods which we can easily apply. In this study, we also use the Google Earth Engine. It is an open source cloud platform, and we don't need to download the data, and we don't need to do any rigorous processing. We can just run some codes, and it can give us our desired results. So I think the paper and the report, they have very good in detail methodology how we can do it, and it is a very simple and straightforward, and it can be applied, I think, almost everywhere in the world, except we have that if we have those kind of a data set about the crop production, crop type data, because the global data does not have the different crop types.
Yeah. So thank you very much, Dr. Abbas. I think just to add on to that, the AC Mode, my organization provides these trainings through the Surveyor program also. We have the Surveyor HKH, and on a regular basis, we do have trainings on Google Earth Engine, application of space technology for crop monitoring, crop loss estimation. So these are provided on a regular basis, particularly for the people in the region, but this could be, of course, shared with wider for other regions too, for their benefit. I will definitely convey this to my colleagues back at home. All right, thank you very much again. Round of applause for you. You get a second round of applause.
Thank you very much, Sandra,
So
for
now,
adding that.
thank you so much. Yes. So let me now go to our last presentation for this particular session. We have this presentation on analysis of drought and flood abrupt alteration events and their agriculture impacts in Kenya. So this is not only floods, but we're also talking about droughts. So you must be curious, what's this drought, floods, alteration, abrupt alteration. So making this presentation, we have Betty McKenna. And Betty McKenna, she is a graduate student at the University of Nebraska, Lincoln. And she's pursuing her master's. So over to you, Betty, for your presentation. I'm sure everybody's eager to hear what you have to say.
Good afternoon, everyone. Thank you so much for this opportunity. So my name is Betty, and I will be presenting my research. I'm doing my master's program, so I'll presenting part of my research, which is analysis of drought, flood, abrupt alternation events and their impacts in Kenya. So I'm looking at a number of impacts, but for this conference, I'm just going to touch on agricultural impacts. Okay, so Kenya is one of the countries in Africa. It's in the eastern part of Africa. So it experiences two seasons, wet and dry season, and the rainfall pattern is bimodal. So we have the long rains during the March, April, May season, and the short rains during the October and November season. The interesting thing about it is that 80% of the Kenyan land is arid and semi-arid. So basically a lot of drought during the dry season. So drought is a big challenge for Kenya, not just in Kenya, but for most part of East Africa. So hypothetically, during the dry season, as I said, it's usually dry. But then during the wet season, there is the land is green again. The water sources are there. So during the dry season, communities go through a lot of challenges because most of the land is arid and semi-arid. We have a lot of pastoralism. So they move from one place to another in search for pastures, long distance to water resources, especially during dry season. And they always look for wet season so that they can do agriculture. They can have enough water for their cattle, for home use and all that. But then the problem is during the wet season, there is that abrupt shift from dry season to the wet season. So the rainfall is not usually, so the rain, other than the rain being a blessing, it's more of a disaster. So I will make a reference to one of the events that really that motivated me to do this research was in 2020. I was in Kenya then. So there was, after a long dry period in 2019, there was all of a sudden a very intense rainfall for one day that killed 20,000 livestock in one day. So this motivated my research, and that's why I'm looking at the impact of abrupt shift from drought season to flood season. So from previous research, compound events have been really becoming a big disaster, not just in Kenya, but globally. So here, I did a research, and from the results, it showed like 11% of drought events have been followed by at least one flood event globally. And also, Zhang from China did an analysis of impact of abrupt shift for tobacco. So my research question will be investigating historical trends of abrupt shift in Kenya, and also looking at the agricultural impacts of this shift. So I'll go to my methodology. So I used CHAPS data, precipitation data, which is gridded data set, 5-kilometer resolution. I looked at three periods. I said Kenya has bimodal rainfall patterns. So from the dry season to the short rains, which is from August to November. So August to September as my drought months, and October to November as the start of the short rains in Kenya. I also looked at November to February. So that's the ending of the short rains to the dry season. And my third season, which is really important, was from the dry season to the start of the long rains, which happens in March, April, May season. So I standardized the data, and then I used an index called Long Cycle Drought Flood Abrupt Alternation Index. And then I incorporated the impact data from the FAO. So I used the crop yield and the animal produce from the FAO yield database. So I'll jump to the results. My first map was showing the abrupt shift from dry season to the start of the short rains. That is from August to November. So from the map, there were two events. So the first one I classified as drought to drought, where the drought in the dry season extends to the wet season, and that is it's visualized in the red shades of color, where the yellow shows there was a little moderate shift, and the red shows there was an intense abrupt shift from drought to extreme drought. So the second one was shift from drought to floods. So that is visualized in the shades of blue, where the lighter shades shows there was moderate, and then the dark shades shows there was intense abrupt shift to floods, and then the gray color shows there was no abrupt shift. So you can see major drought to drought events, mostly in 1983, 1988, 2007, 2013, and mostly from 2018 to 2022, we have had smaller abrupt shift from drought to drought. And then from drought to floods, I will go reference to the most, there was 1997, 2011, 2015, 2019, and 2023. So the spatial patterns of these, most of them are in the northwestern Kenya, Western Kenya, and the northeastern Kenya. So the next map shows the abrupt shift from the dry season to the start of the long rains. The long rains is it's a very important season in Kenya, because most of the farming happens during this season. So then major drought to drought events, 1993, 1998, and then a number of abrupt shift to floods from 2013. You can see a series of blue colors from 2013, 2018, 2020, 2023. One thing you realize is that there's high magnitude of abrupt shift during this season, both for drought to drought and drought to floods. Okay, I correlated my analysis with impact data. So one thing I realized, there was a low negative correlation. I correlated with the drought to floods event. So there was a negative correlation showing like increased precipitation has negative impact on maize and camel milk production. So as you can see, the correlation there was low. One challenge is analysis of impact data, because I was analyzing at country level, and I was taking one value for the impact. Maybe that's why the low correlation is there, but still you can see it's a negative correlation, showing like precipitation is good, but a lot of it has a lot of impact in agriculture. So I'll jump to the conclusion. So there were three major patterns of drought to flood events. So most of them were cumulative across the season. So they start accumulating from OND season to MAM season, and that has a lot of impact to the communities. So one thing I realized is drought to drought events have reduced in magnitude, but increased in frequency. But then the drought to flood events, abrupt shift from drought to flood event have increased in frequency. So just looking at the map since 2012 to 2013, that is like 11 years. Out of 11 years, we've had 8 drought to flood events. So you can see almost every year we have a drought to flood event. So and then we see a negative correlation of impact data with agriculture and livestock. So I sort of updated the slides. So I also had some additional point on adaptive strategies that we can consider for this one. And one of them was the soil management. So I feel like soil erosion, conserving the soil could alleviate this abrupt shift event, because then we can conserve a lot of water that just goes to waste and causes floods, for groundwater recharge, and also for agriculture, because a lot of precipitation is not useful to the communities, but how can we conserve it for drought season? And then incorporation of this abrupt shift into our early warning system. As you can see, the climate is changing. So even our early warning system should be able to change to incorporate compound events, just to prepare communities and to increase our adaptive strategies to natural event as a result of climate impact. Thank you. Oh, so before I proceed, I want to acknowledge my committee members and funding opportunities, Professor Segai, Mark, and Michael, and funding from Fulbright, University of Nebraska, AGU, and of course UNOSA for giving me this opportunity to present here. And of course, Kenya Red Cross, because I was working for Kenya Red Cross before I started my master's program. Thank you.
Thank you very much, Betty, for a comprehensive presentation on your research. Are there any questions for Betty at the moment? I see no hands. I think everybody is getting hungry, a sign towards that. But I have one question. It was interesting to hear, particularly I think we've been hearing quite a bit on floods in general, but what Betty has raised is more the compounding kind of hazards. So it's not only floods, but there is droughts followed by floods, or droughts followed by other different types of disasters. So when you say that it is a way to also prepare the communities well in advance, what aspects of your study looks into preparing the communities? I mean, is it, you said integrating it into early warning systems, but can you elaborate a little bit more?
So yeah, that's a good question. Thank you for the question. So currently I haven't gotten into the integrating into the early warning system, but there is something I want to take up because I do a PhD, just modeling this and incorporating it in the community early warning system. I think that would be a good plus for this research. Otherwise, if it just goes like that, it won't have like that impact to the communities. Yeah.
Well, thank you very much. Again, Betty, a round of applause for Betty. Thanking her for her presentation. Okay, so thank you again to all the presenters online as well as in person. I don't want to take much time in terms of really summarizing what we just heard, but I had several points here that I wanted to just remind us at the end of a very interesting session that we've had. So some of the keywords that we had basically that came out from the conclusions as well as from some of the recommendations that were being brought forth. First and foremost, I think it's important to realize that floods is the most severe hazard. I mean, that's no doubt. When you look at different types of hazards globally in terms of impacting millions, so it's the deadliest hazard in the world. I think we heard this from not only for the first presenter, but also many other presentations that followed. The other point, yes, but it's not only floods, like we heard from the last presentation. There are compounding events. So there are disasters that are becoming major challenges to really work with as well as manage. So it's floods, droughts, landslides, particularly in mountainous terrains. These are different hazards that occur simultaneously. And so you need to be better prepared for multi-hazard early warning systems or multi-hazard kind of ways to respond to that. Now, the other third point that we heard today was also many examples of various tools as well as technologies that came forth that are being used for flood risk reduction, flood management, and in general, water resources management. So examples of, for instance, what we heard from WMO was the FFM program on flash flood guidance system and how it's being used. In fact, Costa Rica is one of the leaders in terms of implementing the flash flood guidance system, which I understand and as well as know, as well as we do have in the Hindu Kush Himalayan region where I come from, a flash flood guidance system in the region, both in Southern Asia, that is being organized or that is being implemented by IMD, as well as for the Western region by the Pakistan Meteorological Department. So the other point was that there's a lot of opportunity for AI and machine learning, and particular examples were given in terms of also looking at ways to link it with impact-based forecasting. I think that is something that is evolving and I think needs a lot of attention, because many times we look at not only what the weather will be, but what the weather will do. So that's where impacts are becoming more important than just saying what is going to happen in terms of the amount of rainfall discharge or the volume of water that is anticipated. Yes, Earth observations fills the existing data gaps. There was examples of for precipitation, for example, the global precipitation measurement data that was used for understanding the spatial extent of the rainfall, as well as the various images from Sentinel data. One of the points that came out strong also was the need for capacity building. So it's not only one-time capacity building, but what we heard was a long-lasting capacity building is essential. So what do we mean by long-lasting capacity building? To me, it is more looking at the institutional capacity building. It should be not at like one of a time, but rather a continuous process of capacity building that needs to be done. That includes training, and that includes various types of capacity building, actually, not only just trainings. Then the question that was asked and also raised was the importance of looking at outscaling and upscaling some of the methodologies and tools that we've heard and examples of today. So how can we learn from the lessons that have been learned in other regions, like, for example, the crop damage estimation presentation that was made from Pakistan? Then definitely, the geospatial tools and technologies, GIS, plays a key role in understanding the risks and vulnerabilities, mapping that, examples that came from Philippines as well as others, which we can use for different types of assessments, and then taking it beyond assessments for more informed decision making. Then I guess the last part was the last presentation really looked at some of the again, the compounding events and how we can integrate it with early warning systems. And that's something that I'm glad, Betty is looking into. And I'm sure there are many other researchers that are looking at these compounding effects and looking at multi-hazard early warning systems. And if you look at the last, the seventh target of the Sendai Framework for Disaster Risk Reduction, it talks about the multi-hazard early warning systems, making it available to everybody. And I think that WMO, they have this target of having the multi-hazard early warning system available by 2027 to all. Yeah, so that's all what we also can strive for, using our space-based tools and technologies to contribute to those big targets. So with that, I thank you all for being here, listening. To those that are online also, thank you very much. And I hope you've had a productive session. So over to you, Nina. Thank you.
Thank you to all the speakers for the very interesting session, and also a great round of applause for Mandira for an excellent moderation of this session. And Harriet, who's contributed online to the moderation. Unfortunately, she couldn't make it here. That was very sad, but we'll make sure to be in touch with her further, and she will also join us for the technical closing session. With that said, and with the delay that we have, I have a suggestion. So we will now start the lightning talk session for the online participants, because the on-site participants have a chance to scan the QR codes outside. We have a poster session where you can individually look into the lightning talks that are of specific interest. Today's lightning talks are all on water quality, which will be the theme of the afternoon sessions. And yeah, with that said, thank you all. And we will continue at 2 o'clock for the session on water quality monitoring.
So thank you all. Nina, if you can just stand here. May I call, I guess, the panelists or the speakers that were present here today for this session, so that we can take a small photograph together. Sorry. Yes, please, Faye. And we have